Picture this. You're sitting in the exam hall. The clock is ticking down, and you've just nailed the final calculation. You scribble down the number, totally relieved, and you move right along. But what you don't realize is you've just thrown away top band marks on a question where your actual physics knowledge was absolutely flawless.
And here is exactly why that happens. Listen to this tragically common 2 out of 10 exam answer. The distance was 4,000, so I added the vectors. Now, contrast that with the 9 out of 10 expectation. The resultant vector requires direction. Distance is 4 times 10 to the power of 3 meters. See, the first student actually understands the underlying physics, but they are speaking completely the wrong language. They aren't speaking to the mark scheme.
Okay, let's dive into this. Why does ordinary standard textbook revision fail so many genuinely smart students? Well, it's because memorizing facts doesn't actually teach you how to write for the examiner. Students constantly lose the easiest marks because they forget standard SI units, they round their numbers way too early in multi-step calculations, they completely ignore vector directions, or they give these incredibly vague practical improvements. Just writing "do it again" to be sure isn't a scientific improvement, right? We need to fix this right now.
Think about the sheer volume of data being processed on a commercial aircraft flight deck. In high-stakes environments like that, precision isn't just optional, it's literal survival. And it's the same principle in your exam. Before any measurement means anything, a standard unit has to be chosen. In physics, absolutely everything we build is based on 3 foundational quantities: length, mass, and time. Units for all other quantities are derived right from those 3. We use the SI system, a metric, decimal-based system used globally, to ensure that whether a pilot is reading an instrument or a physicist is recording data, there is absolutely zero ambiguity.
So, the crucial point here is handling your data safely, especially when your brain is melting under exam pressure. Here is your first quick win. Under pressure, trying to count the tiny zeros in a decimal like 0.004 is just a recipe for disaster. One slip of your pen and you're off by a massive magnitude of 10. Instead, we use the powers of 10 shorthand. 4,000 becomes 4 times 10 to the power of 3. A super small number like 0.004 instantly becomes 4 times 10 to the power of negative 3. Listen, this isn't just about having neat handwriting. This is defensive exam technique. It completely protects your decimal places when you're substituting values into complex equations.
Now, if you truly want to secure those top grades, you need to know what the examiner is secretly asking you behind the scenes. In a moment, I'll show you the examiner clue that changes the answer completely. But first, you need the framework that makes that clue completely obvious to you when you first read the question. Right, here is the exact 4-step framework to bridge the gap between just knowing the physics in your head and actually getting the marks on paper. When you're asked to explain or describe a phenomenon, you don't just dump a messy paragraph onto the page. You structure it. Step 1. State the core physics concept. Step 2. Provide the evidence or data straight from the question, using that powers of 10 shorthand we just talked about. Step 3. Apply scientific reasoning to logically link your concept to that data. And finally, Step 4. Wrap the whole thing in examiner wording. You have to use the precise vocabulary from the syllabus to leave the examiner no choice but to award you full marks.
Let's see how this framework applies to core concepts, starting with physical quantities. A lot of quantities, like force and velocity, have both a magnitude, which is just a fancy word for their size, and a direction. We call these vectors, and this is absolutely critical to remember. When you are combining 2 perpendicular vectors to find the resultant, you cannot just lazily add their sizes together like ordinary numbers. You absolutely must factor in their directions. A scalar quantity just has size, sure, but a vector demands both. If you ignore the direction, your calculation is instantly wrong.
Moving beyond vectors, let's talk about experimental accuracy, because this trips up so many people. Any single measurement you make in a lab isn't going to be perfect. It will always have an error associated with it. Say you're measuring a really short time interval. First, you must choose the appropriate clock or timer. But here's the ultimate examiner-approved method for securing those elusive accuracy marks. Take the average of several measurements, or better yet, measure multiples. By measuring multiples of something, you significantly reduce the relative size of that error. This is a non-negotiable scientific reasoning step you've got to include in your practical answers.
Okay, let's test this out right now. Spot the error in this sentence. The student measured a small distance once and recorded the force as 50. I'll give you a second to spot the fatal flaws here. Think about what we just covered regarding accuracy, measurements, and units.
All right, if you immediately notice that the force was completely missing its unit, newtons, and that relying on a single measurement is a totally flawed methodology, you hit the nail on the head. 50 what? 50 apples? 50 elephants? Without an SI unit, that number is literally meaningless to an examiner. And look at the practical improvement. The vague approach is just saying, measure it again to be sure. That score is a big fat 0. The framework-approved answer applies real scientific reasoning. Take the average of several measurements to reduce the size of the error. Notice the precise examiner wording in that second version. That's what gets the marks.
I like to call this next part the examiner's red pen. This needs to be your mental checklist before you ever hand in a paper. Ask yourself, are your graph axes actually scaled correctly and labeled with the right units? Did you substitute the correct variables into the equation? Is your final conclusion genuinely supported by the data table, or did you just kind of guess based on what you thought should happen? And the most painful mistake of all, did you leave your final answer floating there completely naked without an SI unit? These are the unforced errors that drag top-tier students right down into average grade boundaries.
Which brings us to the absolute most frustrating scenario in all of Cambridge physics. Imagine this. You've used the powers of 10 shorthand perfectly, you remembered all your vector directions, you averaged your multiple measurements to reduce the error just like we practiced, your physics is 100% correct, but your mark is still a 0. Why? How is that even possible?
Because a perfect physics calculation absolutely fails if you misread the command word. Knowing the concepts and having that 4-step framework is incredibly powerful, yes, but it's completely useless if you apply it to the wrong task. If the examiner explicitly asks you to evaluate, but you only describe, you failed the question before you even picked up your calculator. You now have the framework to structure a top-band answer, but if you misread the command word, you'll still lose the marks. Click the video on screen right now to decode the exact Cambridge command words that decide your mark band. And remember, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations.